started the recording. Yeah, okay. So the problem is that we have say a 3 centimeter internal dia, okay, and a 5 say meter long pipe. Okay, say the water is flowing at a certain temperature. Say it is 15 degrees centigrade. This surface of this tube is, say, we have a jacket, heater jacket that is wrapped on this. Okay, so say we have a heater jacket that is, we have a wrapping on this surface that is providing a constant surface heat flux. Okay, so the water that is entering at 15 degrees centigrade is coming out at 65 degrees centigrade. Okay, so this is a steady state scenario. Now say if we have to supply what we have to, so these are the two boundary conditions, or say the two conditions that are maintained in the system. And now if we have to vary the flow rate, okay, say water is flowing at a certain meter per second, the velocity, superficial velocity, or if I say that certain liter per minute, which is the volumetric flow rate. Now there would be a power requirement in order to handle that. So if the flow is, say, at lower flow rate, if the power requirement is P1, if the flow is at higher flow rate, then naturally that we have a given constant that the length is 5 meters, diameter is 3 centimeters. So if flow rate is higher, that means we have to ramp up this power that is jacketed at the outer surface of this tube. Okay, so now say we need at least 10 liter per minute this flow rate. Okay, this amount of water has to be treated from 15 to 65 degrees centigrade. So the question is, what is the power requirement that you have to put in this jacket, the heater jacket? This is the part 1, that heater power that is required in order to achieve this condition. And part B, that what would be the inner surface temperature, inner surface temperature. Now at first tell me whether my question is correct or not. If the question is correctly posed or not. Did you get my concern?
Yes, sir, but little doubt on inner surface temperature. Like you are saying, it is constant surface heat flux. Okay, we will find that.
No, okay, you will find that. That is my point. Is it the right question that I have asked, or is it something wrong in the question? That itself is the first question, say, for this problem. That I tell you that there is a constant surface heat flux that is being provided by the jacket. And then again, I'm asking that what is the inner surface temperature? Will you not argue on this point that it cannot be?
So we have to
Like,
first find the Reynolds number, like if it is in turbulent
So
zone or
forget about Reynolds numbers. Forget about the Reynolds number. That was the logic of the question, the basic thing.
like we are having only inner diameter given, and we
Hmm.
are considering the tube to be like very thin, like inner diameter
Hmm.
and outer diameter are approximately equal.
Okay.
So
Okay.
there will be no question of inner surface diameter and outer surface diameter.
That is fine.
Right,
That's
temperature.
perfectly fine. That's perfectly fine. But my question is that, I mean, I'm not asking about that kind of tricky question or trick questions. My question is about this last part particularly. Let me give you the hint.
We cannot have constant heat flux and constant surface temperature together at the same time.
Right. So that means here something is missing. That, or it's an incomplete information. That inner surface temperature, it is not constant throughout the surface. If you have to keep the constant surface heat flux and your inlet and exit temperature are fixed, then how can you maintain a constant surface temperature? That is not possible. So it has to be suffixed by a point that where you need the inner surface temperature. So the question is now rephrased as the inner surface temperature at the exit. Where the fluid is having 65 degrees centigrade, what is my TS at this exit? These are the two questions. Shreyandu, did you get this point now?
yes, I was thinking about we have to find surface temperature as a function of length of tube.
No, no,
So that's
that's not the point. If that has to be, then you have to mention that either what is that per unit or it's a surface temperature variation or something like that you are mentioning. It's not that whatever I'm asking is true without having your doubts clear.
yes, sir. Now it's clear.
Yeah, good. So please go ahead and solve this. But for this, you need a couple of physico-chemical parameters, or say the properties. Okay. So the properties of water, let's consider density as 992.1, just to have your calculations complicated, because it's a straightforward problem. And also these, so again, when I write this thing, I'm telling you directly these values, but there is a way to get these values. In fact, how do you get this? You have to find a table where the water properties are mentioned, kind of a steam table or something like that. And there you find a particular temperature on which you have to estimate, you have to read out these values. So the temperature would be what? At which temperature you would look out for these values?
Bulk mean temperature.
Bulk mean temperature, which is 15 plus 65 divided by 2, which is at 40 degrees centigrade. At that case, the rho of water is this value. K is having 0.631 watt per meter degree centigrade. Nu, okay, it is 0.658 into 10 to the power minus 6 meters square per second. Cp is 4179 joule per kg degree centigrade. Prandtl number is 4.3432. These are the properties you would need to complete the calculation. So how do we proceed?
First, we have to calculate the flow velocity by flow rate. Then we have to find the Reynolds number, and then accordingly, if it comes in laminar, then we have to apply laminar formula. Otherwise, the turbulent zone.
That what that would give you?
So 1 minute, let me think a little more. Like if it comes like in laminar, like we have to find for the constant surface heat flux Q dot S, and that will be like a power requirement. According to it, we have to find first H, and then T min is there with us by LMTD, TS.
See, one thing there is, in order to calculate Q dot, you need HA del T.
Yes, sir.
Now here H is also unknown and Q is also unknown. So there is information given that you can estimate the Q dot even without calculating H. How do you do that?
By like heat capacity of liquid, we
Right.
can do it by flow rate.
Right. So that means you have a known flow rate. Okay, you know how much temperature we have to increase. That means how much heat flux we have to provide. That is by mCp delta T, or say m dot Cp delta T, if it is mass flow rate.
Yes, sir.
That is your heater power, in fact. That much energy you have to constantly supply. So the first point is that what is my mass flow rate?
Rho into flow rate in standard units we have to put.
Others are doing. We'll call out the name then. Do not just sit idle. Varun Balakrishna, are you following the problem?
Yes, sir, I'm doing.
Okay, so tell me, what is the mass flow rate? In value, in numerics. That's very simple. What is my mass flow rate?
So 10 liter per minute into the area.
Yeah. So what area? Okay. What is the area?
Pi 3 square by 4. So all the already given.
So volumetric flow rate multiplied by area, what it would give you? What is the unit of volumetric flow rate in SI?
kg. So kg meter square per second.
Volumetric flow rate, Varun.
So 1 second, sir, I'm getting confused. So you're given 10 liter per minute is the.
So I am asking what is the unit of volumetric flow rate in SI, because you have to eventually convert everything into SI unit.
Yes, sir.
That is the first lesson we have learned in CPC and where you scored highly.
Yes,
So
sir.
that is why my concern now is that.
So it's meter cube per.
The volumetric flow.
Sir, it's meter cube per second.
Okay. So how do we convert liter per liter to what is the relation between liter to meter cube?
1 liter is so 1 liter is 0.001 meter cubic meter.
0.001 or 0.01?
1 liter is 0.001 cubic meter. So 10 power minus 3.
10 power minus 3?
Yes, sir. So 1 liter is 10 power minus 3 cubic meter.
Okay.
Yes, sir.
Yeah. So go ahead with now the calculation that what is my m dot, the mass flow rate.
So is the answer 34.55 kilowatt?
34 point. Yeah, approximate. Right. 35.55 means 35.6. Right. Perfect. So step by step, let follow. Let the others follow as well. So how much did you get? Okay, Deepjoy rather, not Deepjoy. Deepjoy Bashak. Are you following? If not, see Deepjoy, I am not at all taking the attendance as well. So you can just peacefully sleep. No one would bother you. Rakesh. Rakesh. Okay. Shraman Pal.
Yes.
Yeah. So what is the mass flow rate value?
1.65 kg per second.
1.65 kg per second. Sure. Srinivandhu, did you get the same value?
So I've calculated the final value. Now I'm calculating one.
No, without calculating m dot, how can you put it in CP delta T?
Like I have calculated the whole expression. Like
okay.
Finally, it is like 0.16535.
Yeah, it will be 0.
So
I missed the point.
It is coming around 0.165.
0.165 kg per second. So Shraman, check your decimal.
Yeah, I missed a 1 point for the row.
Right. Good. Okay. So that gives you the Q dot value, which is m dot Cp delta T. The values are already here. So this would be around 34.6 kilowatt. And again, K is small k. So this energy must come from this heater jacket. Now the question is, what is the surface temperature at the exit? How do you do that?
Like we know this Q dot. So
Yes.
we will find TM by LMTD. If we able to find HX, then it is easy job for us.
So how do we do that?
We find QS, like Q surface heat flux. And
The
then,
surface heat flux.
yes, sir.
Okay, so how do we find surface heat flux? Say if I write Q dot F, this one that we have calculated, this is the heater power that should come per unit surface area. Okay, and what is AS?
Pi D into L.
Pi D into L, absolutely. So we have 34.6 and here pi D L. Pi D into L. So kilowatt per meter square. This would be around 73.5, right?
Yes, sir.
Yes, sir.
73.4. Yes, sir.
Yeah. Okay. So then Tridipta, are you there?
Yes.
Yeah, Tridipta, go ahead. So next step, what is the relation between Q dot S and TS, or say
So dtx
yeah.
of ts is equal to a constant which is q dot s into p by m dot into cp.
No, so that is the fluid calculation that we have done, that mcp delta t, because the fluid is gaining temperature or gaining energy, and how much energy it should gain, that is the heating power. Now we know when there is constant surface heat flux condition, okay, that this q dot s is basically what happens, h ts minus tm, because the mean fluid temperature is changing. If we take that it's the mean fluid temperature at that location. Fine. Now this T mean at the exit is the exit temperature, which is 65 degrees centigrade. At that location, our question is what is TS? This is the question. This Tm is 65 degrees centigrade at the exit. We know Q dot S. We can find TS if we can estimate the value H. And now in order to estimate the value H, we have to calculate the Reynolds number. We have to see, because Prandtl number is given.
So before that, we have to like just find a lot of conditions, like whether it is in laminar region or it is fully
Yeah, so
developed
that is
flow
what I am
or
asking. That
not.
now we have to find that what is the Reynolds number. That would tell us several stories, or what are the next step would be.
So your voice is breaking. I don't know for me or.
Now is it fine? Can you
No,
guys?
sir.
Yes, sir, it's clear for me.
It's clear for you.
I think it's
Okay.
come from my side.
Okay. Yeah. Your voice is in fact breaking. Okay. Okay. So now the point is, what is the Reynolds number? Shayan Haldar, it's your turn.
Sir, I have not attended the last class. Therefore, I have some
But
problem in this.
without attending that, you can calculate what is the Reynolds number.
Okay,
for
sir.
a
Okay, sir.
pipe.
Okay, sir. I will do now.
Yeah.
Sir, can you please scroll up for the property values? I didn't notice that.
Okay. Okay. Yeah. These are the values.
So it's in turbulent region.
What is the value? Tell me the numeric.
So it's approximately 1 minute. So it is 10,942.
In the order of 10,900 that you are telling.
Yes,
Okay.
sir.
Okay. So how did you calculate that? What is the V that you have calculated?
So V is coming as 0.24 meter per second. By flow rate, we can calculate it.
Right. So the V that you would calculate is basically volumetric flow rate divided by the cross-sectional area. That is
Yes,
10
sir.
liters per minute, which you convert to meter cube per minute or meter cube per second. And you have a cross-sectional area, which is pi d square by 4. Pi here d is 0.03. By that, you calculate your V. That would come around what he mentioned is in the order of 0.24 meter per second.
10,900.
Using that value, yeah, so almost in the similar magnitude, but that would be used later. So how much precision we have in this value, that would dictate our H value. So the point is now, that means we have the V or the V mean, whatever, or the V superficial, whatever you can name it, d by nu. That is my, this is my Reynolds number. Substitute the values here, you get this thing. So which is in the turbulent region, because we know the critical Reynolds number for a pipe flow is around 2100. Okay, after that it becomes, there is a transition period, and then we have turbulent when it is more than 10,000. Is kind of a fully turbulent valve. So if that is the case, then we had several conditions, if you remember, that now we have to see whether it is the length of the pipe that is given here, is it sufficient that fully turbulent flow or fully developed turbulent flow can be considered, because based on that we had our Ditters-Boelter equation, or say the Kohlborn equation. There were several things were there.
So for, like you told, for turbulent zone, it is, if the length is 10 times d diameter, then it is
Right.
sufficient. And
Right.
here it is 10 times d will be 30 centimeter, which is very much less than 5 meters.
So
So it is sufficient.
which is very much lesser than the pipe length given, which is kind of a very negligible distance. So it is that we can safely assume that the flow is fully developed turbulent flow. Okay, because the entry length is in the order of 10d for turbulent flow, which is around 0.3 meter. Now here the pipe length is itself given 5 meters. That is kind of a negligible portion compared to the complete or the whole length. So we can apply Dietz-Boelter equation for calculating the Nusselt number and subsequently the heat transfer coefficient or the convective heat transfer coefficient. So now someone tell me that what is the Dietz-Boelter equation? Look at the last note and tell me what is the Dietz-Boelter equation.
Nusselt number is 0.023, Reynolds number to the power 0.8, Prandtl number to the power 1/3.
So the coefficient,
Take your time.
so the
Take
power
your
of
time.
Prandtl number will be 0.4.
Absolutely. That is why I asked you to take your time. Because the reason is that now there was a condition, if you remember, that 0.3 for cooling and 0.4 for heating condition. Now here the fluid is being heated. Okay, so the coefficient would be 0.4, or the index here would be 0.4. The coefficient and Reynolds number, these things would remain same. So this part actually leads to the mark difference whenever you use it. If you use it casually, that would lead to the error. And then you argue that I have used the Dietz-Boelter equations, but still my mark is deducted. So this should give you around, say, in the order of 70, if I am correct. The Reynolds number you have already calculated. Prandtl number is given.
70.1.
Yeah. So that's why I mentioned in the order of 70. Okay. So which means now we can calculate what is my H, which is K by D multiplied by the Nusselt number. And that comes out to be Rahul Goldar.
Yes, sir.
Are you following?
Yes, sir.
Okay. So what is the
H
value of
is,
H?
H is coming out to be around 8.878.
H? No. Check the calculation.
So can you
have
scroll up?
K value is 0.631. Let me write it quickly. D value is 0.03. Okay. And you have this multiplied by 70. So how can that be 8 point something?
Around 1475.
1479.42.
1479.
79.4.
Okay. Okay. And the unit would be, Bhavna?
Yes, sir. And the unit for it will be in joule, means in SI, should I say now?
No, in unit of H. This is the H at that time calculated.
Unit of H should be joule per degree, sorry, watt per degree C.
Watt per meter square. Watt per meter
Per
square.
meter square degree C.
So H is calculated, and then what? What is the surface temperature? Now we go back to this expression. And from here, what we can write? This expression means this highlighted one. What is T surface? Is T mean at that fluid location plus Q dot S by H, which is 65 plus Q dot that we have already calculated. What was the Q dot value?
It was
So
73.5 kilowatt.
73500 watt per meter square.
It is 114.68 degrees Celsius.
By 1479. Watt per meter square degree Kelvin. So this is also degree centigrade. So this comes out to be how much?
114.68 degrees Celsius.
115 degree centigrade. This range. Any question, guys? Anyone? So somehow someone calculated this value to be 60 degrees centigrade. Should you be able to tell directly that the answer is wrong without even checking anything, the calculation?
Like
So
for
because
if it is
P,
heating, like so the surface temperature would always be greater than the bulk temperature, like fluid temperature. So if it is the fluid is exerting at 65 degrees Celsius, so obviously the surface temperature should be greater than 65 degrees Celsius.
Right. So this is one point where you can quickly realize, if you give a pause, that whether my answer is correct or not during the answering in the exam. That this surface temperature, it would not cross that value. I mean, this value has to be sufficiently higher because the heating phenomena is going on. So tell me now, based on your understanding of the theory, say this temperature difference, okay, how that would vary in the fully developed region. So here we have a temperature difference of 65 to 115 degrees centigrade. So here we have 65 degrees centigrade and the TS is 115 degrees centigrade. So our eventual del T is 50 degrees centigrade. Now my question is, after say immediate this 0.3 meter, which is around the entry length in the fully developed turbulent region, what would be the del T value? So as surface temperature is changing, also the mean temperature is changing. What would be the profile of del T along the X?
Exponential.
Think about it.
sir, could you
are
repeat?
In the fully developed region, that means after say 0.3 meter from the entrance till the rest of the length, what is the del T profile along X?
So delta is like Ts minus Tm, and we know Tm varies as TS plus exponential part. So it would be del T will be something exponential part on
So it will be a horizontal line, you think?
Right. It is a constant value. See, Snehamundi, if you look at this expression once again that you are mentioning, we are calculating H. There is a different way to think about this. One of the ways is that you are calculating H in the fully developed region, which is a constant value.
Yes, sir.
Your Q dot S is constant.
Yes, sir.
So del T has to be constant.
Okay, sir.
So del T is straight line. That there would be always a difference of 50 degrees centigrade along the length of the pipe in the fully developed region. So in such cases, in the fully developed region, temperature gradient is always constant.
So like it's a way of calculating the temperature difference. Like we can calculate at the end or at the beginning. So it would be same for all.
Yeah. But at the entrance that I said, that at the very near that till 0.3 meter that you calculated or it is estimated, because this part is required for the flow to be developed in a fully turbulent region, fully developed flow. In case of turbulent flow, that is the length we typically give it. So if I ask you that what would be that temperature profile point from 0.5 meter to 5 meters, you can safely draw a horizontal straight line where del T is constant and the del T value is 50 degrees centigrade.
Yes, sir.
Okay. Now we quickly move on to the other problem. We have 5 minutes left. We can do possibly if you quickly do the same thing, or you can take the same values nearly. Okay, let me tell the problem. So here the problem is that we have say a rectangular, or say so we have say a rectangular duct in which the air is flowing at 80 degrees centigrade. Okay, atmospheric pressure. Okay, so instead of rectangular, consider this as a square cross section. So this is 0.2, this is 0.2 meters. Okay, both the sides are, so cross section is 0.2 by 0.2 meters. Okay, so the air is flowing at a rate of 15.15 meter cube per second. Okay, this surface, say, it is isothermal and is at 60 degrees centigrade. What is the exit temperature of the flow and the rate of heat loss? So Ti is this. The question is, what would be our T exit when it go out? The length of this duct is say 8 meters. The properties, let me give you. Say rho is, in this case, you can consider 1 kg per meter cube. The air density. Just for the sake of quick calculation, K say 0.03 watt per meter degree centigrade. Nu, say I give you the value of 2.1 into 10 to the power minus 5 meters square per second. Cp is 1008 joule per kg degree centigrade, and Prandtl number 0.71 Okay, 0.72. Similar problem, but now we have a constant surface temperature. So tell me what is the TE, exit temperature. We follow the similar strategy or the steps.
Like, so first we will find the Reynolds number again, like to check whether it is in
And
touch.
what is the Reynolds number? What is the value of the Reynolds number?
Yes, I do. Like I'm asking the approach, like if we find the
Sure.
number,
Right.
then
So definitely we
by
find the
that we-
Reynolds number
by that we will find H, value
by
of H.
saying we see, okay, once we find the Reynolds number, we again check whether the sufficient length that has been given
Yes, sir.
for to consider the fully developed case or not.
Yes, sir. And
Now,
then we just apply that formula of T mean is equals
right.
to
I
TS.
mean, in this case, let me tell you, the Reynolds number is in the range of 35,000, which is quite, I mean, it's kind of a very turbulent flow, I mean, fully turbulent flow. And then the
Yes, sir.
entrance length is 10 times D, which is here 2 meters, because we have a cross section of 0.2 meters.
Yes, sir.
The length is given as 8 meters. So we still consider that the fully developed flow in the entire duct. So to determine the Nusselt number from the Dietz-Boelter equation. Now remember here the air is being cooled.
Yes, sir.
Because you have a 80 degree centigrade, the surface temperature is 60 degree centigrade, which is isothermal. So that means air will be cooled. That means in Dietz-Boelter equation, the Prandtl number index would be 0.3, not 0.4.
Yes, sir.
Then you calculate Nusselt number, you calculate heat transfer, convective heat transfer coefficient. Okay, and then you apply that the exit temperature point, which is that we have the exponential decay, right? If you remember the graph where
Yes,
you
sir.
have minus HAS by MCP in the exponential.
Yes.
So we apply that equation. The equation is, or the expression, those who forgot, they can remember that my T exit minus TS, or say the TS minus T exit. Okay, so it is kind of, if I write in terms of say TS minus T exit divided by TS minus TI, this equals to exponential of minus HAS by M dot Cp. This would give us the value of TS, the surface temperature. Sorry, not surface temperature, it is given that value of TE.
Yes, sir.
Which would be in the order of numerically close to 70 degree. And then what? The final step, to calculate our exit temperature. Or say, sorry, the exit temperature we have calculated. What is the heat rate that is being lost? The rate of heat loss. What is the formula?
MCP delta T we will apply.
M dot Cp delta T. And if you try to use, so why did you calculate the value of H? It is for this point, right?
Yes. Yes,
And
sir.
you still try to apply the Q is equals to HA delta T relation. What would be that value? What would be the delta T in that case? For the constant surface temperature, what is the delta T?
LMTD.
LMTD. So if someone applies this thing, this would be LMTD. And that LMTD would be calculated based on this inlet, outlet, and surface temperature. So if your calculations are right, I told you the value in the range of 70 degree here, and here you would get in the range of 1300 watt with a negative value. That means this is being lost. Any question?
No, sir.
Anyone? Bhavna, did you understand? Okay, guys, then thank you. I overshoot 5 minutes again.